Definition of the derivative at x equals a. We are now about to enter one of the two main branches of calculus, differential calculus, which is based on the notion of a derivative. So, what is a derivative? When you hear the word derivative, I want three things to immediately come to mind. Number one, that the derivative is a limit of a difference quotient. Number two, the derivative represents an instantaneous rate of change. And number three, the derivative at a point is the slope of the tangent line at that point. Now, even though I have numbered these as 1, 2, and 3, they are all equally as important. And the first one that we're going to take a closer look at is that the derivative at a point is the slope of the tangent line at that point. So we just defined a derivative to be the slope of a tangent line. But what is a tangent line? Informally, a tangent line to a point on a curve is a straight line that only touches the curve at a single point near that point and grazes the curve. So to understand this better, let's take a look at this image off to the right. So here we have this black curve and this point a f of a on the curve. To find the tangent line to the point a f of a, I would need a straight line. So this red line satisfies that requirement. I have a straight line that only touches the curve at a single point. So there's that single point where I touch the curve near that original point. So this point right here actually has a special name. It's called the point of tangency. And what I want is I want my tangent line to only touch the curve at that point around the point a f of a. Now, what I mean by that is that this curve could turn around and come back down, and this line here would keep going and actually intersect somewhere else, but that's fine because it's not near the original point, the point of tangency. And we want to make sure that the tangent line also just grazes the curve. So what I mean by that is that a line like this that just sort of cut straight through would not be considered a tangent line. The tangent line has to just softly sort of graze the curve and touch at exactly one point near that point of tangency, although it can intersect somewhere else as long as it's not near that important point. So the idea is that we're trying to find the slope of this tangent line. So right, any line has a slope, and in order to find the slope, hopefully you're thinking that we're missing something, that we're missing an additional point. So we have a f of a, we have a xy or an x1, y1, but we don't have a second point on the line. So that brings us to the notion of a secant line. So what we're going to try to do is we're going to try to use a secant line, which by definition crosses a curve at 2 points. So looking at this image here, we have the original point a f of a. And then we are going to go ahead and just define some other generic point. We're going to call it x f of x. So now I have 2 points, and both of them lie on my curve. And if I connect those 2 points together, I'm going to form a straight line, and you can see that line is called a secant line. And between any 2 points, I can actually find the slope of the line. So remember, I'm using the formula m equals y2 minus y1 over x2 minus x1. So in my case, I'm using the points x f of x and a f of a, very generic. So my slope between these 2 points is going to be f of x minus f of a, so my y2 minus y1 over x minus a, my x2 minus x1. And so you'll notice that off to the right, there is actually a special name for each of these differences in the numerator and the denominator. So the title of the numerator here, or the label we've assigned to it, is delta f. And this delta symbol here means change. So the difference between the y values, or the function values, is the change in f. So f of x minus f of a. And then the difference between the x values, the x and the a, is represented by delta x, the change in x, x minus a. And this quotient here actually has a special name. So let's go ahead and scroll down a little bit. It is called the difference quotient. So the expression, the change in f, or the change in y, all over the change in x, or f of x minus f of a over x minus a, is called the difference quotient. And if you remember, the first thing I wanted you to think about in terms of the derivative is that the derivative is the limit of a difference quotient. So now we're going to try to make that connection, that the derivative is the slope of a tangent line, and we're going to try to make the connection that the derivative is also the limit of a difference quotient. So the difference quotient meaning the change in the y values, or the function values, over the change in the x values between 2 points on the curve. The goal is that we want to use secant lines to find a tangent line. So let's look at this progression of images to see how that might work. In this left image here, the blue line that goes through points P and Q is the secant line. It goes through 2 points, so we can very easily find the slope of this blue line. However, our goal is to find the slope of this pink line, and we only know 1 point on the pink line. Now the next thing I want you to notice is that the secant line has positive slope, and so does this tangent line. But the slope of the secant line is just a bit steeper than the slope of the tangent line. So if we were to try to use the secant line slope as an approximation for the tangent line, we wouldn't have a very good approximation. But we arbitrarily chose this point Q on the curve. So what if we just went ahead and moved Q a little bit closer to P? So on the x-axis, it's like moving this x value just a little bit closer to A. Now hopefully you see that the slope between the 2 points P and Q is a little bit of a better approximation to the slope of the tangent line here. It's not quite as steep as the previous graph. So let's go ahead and move Q just a little bit closer to P. So move X just a little bit closer to A. And you'll see that the slope of the secant line is just a little bit closer to the slope of that tangent line. And so this final image here shows that as the point Q gets closer to the point P, or on the x-axis as X approaches A, all of these secant lines get closer and closer to the tangent line at the point P. So hopefully you sort of heard the key phrase that X is approaching A, and you think of the concept that we developed first, the notion of limits. So that's how we're going to relate the notion of limits to the concept of derivatives. So we're going to use secant lines and the notion of X approaching A to help us find the exact slope of the tangent line using these secant lines. So this is written out for us in the pictures above. Notice that as the point Q moves closer to P, the distance between A and X is getting smaller, and the slope of the secant lines are looking more and more like the slope of that tangent line that we're in search of. Alright, so now we want to formalize the definition of the derivative at a point using secant lines. So we said that our goal was we were going to try to use this secant line here between points P and Q to find the slope of the secant line right at the point P. And the idea was that we were going to take this x value and move it closer and closer to A. Well, we're going to come up with an alternative way to think about that concept. So what we want is to think about the distance between X and A. So let's go ahead and call that distance H. So if this first point is A and this distance here is H, then this coordinate X is A plus H. So now we have this point here at P, which is A f of A. And if we call this distance here H, then this x value is A plus H, so this coordinate point is A plus H, f of A plus H, and it's a coordinate point. So now our difference quotient is going to become y2 minus y1. So using the slope between the secant line, we're going to have f of A plus H minus f of a all over x2 minus x1. So a plus h minus the x1 value is a. So now the difference quotient is going to simplify when the a and the minus a cancel to become f of a plus h minus f of a all over h. So this is equivalent to the other difference quotient definition that we arrived at. It's just an alternative form. And it's the reason why we're going to develop it is because it's a little bit easier to think about. Instead of x getting closer to a, we really want this distance that we called h. We want this distance to go down to 0. So if this distance ends up shrinking all the way down to 0 or approaching 0, then that's going to help us find the slope of the tangent line at the value of p. So the new difference quotient that we're going to take a look at, although we're not going to forget the previous one, is that the change in f over the change in x, or again, the change in y over the change in x, is f of a plus h minus f of a all over a plus h minus a, which is nice because the denominator simplifies to just h. So now we've reached the point where we can finally formally define a derivative at a particular point x equals a. The derivative of a function f evaluated at x equals a is the limit of the difference quotient. So the notation here is that f prime of a, so this is some new notation, f prime means derivative. So this is the derivative of f at the x value a equals the limit as h approaches 0. Well, remember, h was that distance on the x-axis between the 2 points, so that distance is going to 0, of the difference quotient, f of a plus h minus f of a all over h, provided that the limit exists. So remember, we had some cases in limits where the limit failed to exist. So if this limit yields a real number, then we have a derivative at the point x equals a. And when the limit exists, we have some new terminology that f is differentiable at x equals a. So an alternative formula for the derivative at x equals a is given by the limit as x approaches a of f of x minus f of a over x minus a. So this is using that alternate form of the difference quotient. So we want x to get closer to a, so that corresponds to this picture here. As the x values are getting closer and closer to a, then the secant lines are used to find the tangent line. And then this left image corresponds to the fact that we would want this h that we defined as the distance to go closer and closer to 0, so that the point Q gets closer and closer to the point P, and we still find that tangent line. So they are equivalent definitions, but it is important that you know both of them because both of them appear in different forms and throughout many different problems. Alright, so let's take a look at an example of how we would find the derivative of a particular function, f of x equals x squared, at x equals 3. So I just want to go over a couple of different ways this problem could be asked. We could also have been asked to find the slope of the tangent line to the function fx at x squared at x equals 3. Or we could have been given the function f of x equals x squared and been asked to find f prime of 3, because this notation means find the derivative at the particular point x equals 3. So before we even plug anything into our formulas here, our equivalent formulas, let's take a look at, on a graph, what we're actually trying to do. So the curve is x squared. So hopefully we remember what x squared looks like. So let's go ahead and sketch the function here. So here's our curve. It's a parabola. And if we're trying to find the derivative at x equals 3, so let's just say here's the x value 3, and we'll go up to the function at 3. And what we want to do is find the derivative. Well, the derivative is the slope of the tangent line. So let's go ahead and sketch the tangent line. It's only going to touch at that point of tangency there. And it's going to just graze the surface. So our tangent line is going to look like this red line here. So we're interested in finding the slope of this line. That's what we're about to find, the slope of this particular tangent line at x equals 3. So hopefully what we should know at this point is that it definitely has to be a positive value because this tangent line here has positive slope. So what we're going to do is we're going to use both definitions of the derivative here to find it. So let's go ahead and plug in our values. Our a value is going to be 3, so we're in search of f prime of 3, which is the limit as h goes to 0 of f of, so in place of a, I went ahead and put the number 3, so in place of this a, I'm going to have to put the number 3. So f of 3 plus h minus f of 3 all over h. So now I want to solve this limit. Well, f of 3 plus h, so just this portion here, f of 3 plus h, means that I'm going to replace, so here's my function, f of x equals x squared, I'm going to replace my x value with 3 plus h. So this portion is going to become 3 plus h squared. So all I've done is f of 3 plus h, which means take 3 plus h and plug it into x and square it. So 3 plus h squared, and then minus f of 3. So f of 3 means I'm going to take the 3 and plug it into the x. So minus 3 squared, and then nothing changes about the h, that just stays h, and we're still doing the limit as h goes to 0. So now we've reduced it down to a limit problem where if we try direct substitution, we're going to have a problem. So if we substitute 0 into this h right here, we're going to have 3 squared minus 3 squared, so 9 minus 9 is 0, and substituting 0 in for h on the bottom, we'd get 0 over 0. So we have our indeterminate form, so we're going to have to do some additional algebra. And the additional algebra is that we're going to have to expand the quantity 3 plus h. So 3 plus h times 3 plus h is going to become 9 plus 6h plus h squared. So all I did was distribute 3 plus h squared. And then minus, well, the 3 squared quantity is 9. And then we have all over h. And this is still the limit as h approaches 0. So let's give ourselves some more room here. So now notice what's going to happen is that the 9 is going to cancel with the minus 9. And in the numerator I have 6h plus h squared. And in the denominator I have h. So I want to get rid of the h on the bottom. So I'm going to factor an h out of the numerator. So h times 6 plus h all over h. And we still have a limit as h approaches 0. So let's go ahead and cancel the h values. So what we're left with is evaluating the limit as h approaches 0 of 6 plus h. Well, now if I substitute in 0, I'm going to get just 6 plus 0, which equals 6. So what we started out with is that f prime of 3 was this limit which exists because it has a numerical value of 6. So what we found is that the slope of the tangent line, back up here, is of slope 6, right at the x value x equals 3. So that was using this definition of the derivative with this particular difference quotient. But let's try to also use the alternative definition of the derivative. So let's go ahead and substitute everything in here. So I'm still trying to find f prime of 3, which is the limit as x approaches. In replacement of a, I'm going to put my value of 3. And now I need to do the difference quotient f of x minus f of a, my a value is 3, all over x minus 3. So now let's keep going with this limit. The limit as x approaches 3 of, well, f of x, if you remember, we can scroll up. F of x was x squared. So in replacement of f of x, I'm going to go ahead and put in x squared. and then we're going to do minus f of 3. So f of 3, just like we found over here, is 3 squared. So x squared minus 3 squared over x minus 3. So we'll give ourselves some more room here. We have the limit as x approaches 3 of x squared minus 9 over x minus 3. Again, this limit now, we can try direct substitution. So we get 3 squared minus 9 over 3 minus 3. So we get 0 over 0. We're going to have to do some more algebra. The algebra this time involved is factoring. So in the numerator, we're going to get x minus 3, x plus 3. The denominator had the quantity x minus 3. So these two linear terms will cancel, and we still have the limit as x approaches 3 of x plus 3. And now we can substitute in our 3 for x. So this is 3 plus 3, which gives us the value we already knew was the slope of the tangent line, 6. So this was using either definition of the derivative to find the slope of the tangent line to the curve x squared at the x value of 3. Alright, so now we're being told that the following limits represent derivatives of f of x at some x equals a value. Find f of x and x equals a. So there's sort of a tricky set of problems now that are going to exist because we originally were used to solving limit problems, but now we have these derivatives that look like limits because derivatives are limits of a difference quotient. So what you're going to have to recognize is when a limit represents a derivative. Now this set of problems is telling you these limits represent a derivative, but let's try to look at each of these problems and see if we could have decided for ourselves that these represent a derivative. So we're looking for either of the two forms, the limit as h goes to 0 of f of a plus h minus f of a all over h, or we're looking for the limit as x approaches a of f of x minus f of a all over x minus a. So we're looking for limits that look like either of these two forms so that we could call them out as derivatives. And then we're going to try to find the function that we were originally trying to take the derivative of and the a value, the point that we were trying to find the slope of the tangent line for. So this first problem, the limit as h goes to 0. There's my first indication right there, is that I have to have these definitions memorized so that I could recognize that h goes to 0 is a huge indicator that this is a definition of the derivative limit. So the limit as h goes to 0 of f of a plus h. So notice a plus h, a huge giveaway for the value of a is whatever number is being added to h. So again, we're in search of f of x, and we're in search of x equals a for each of these problems. Well, my a value is the one that is being added to the h. So x equals 2. 2 is my a value. So now it's a matter of trying to figure out, well, what's f of x? So we decided that a was 2, so what function are we plugging 2 plus h into? Well, we're plugging 2 plus h into the function x cubed. So the limit as h goes to 0 of 2 plus h cubed, so this is a plus h being plugged into the function x cubed, minus, so this quantity right here, so let's just kind of mark it all up on this first one. This is f of 2 plus h, so that must mean that 8 is f of 2. Well, to check, if we substitute 2 into x cubed, 2 cubed is 8. So this numerator does in fact represent f of 2 plus h minus f of 2 all over h. So the answer to this first problem is that f of x equals x cubed and x equals 2 is my a value. So now let's take a look at this second problem. The limit as h goes to 0 of the square root of 16 plus h minus 4. So that h goes to 0 tells me that this is a derivative problem. And the a value, again, the easiest way to find it in this case is to recognize that the a value is what's being added to h. So x equals 16 is my a value. So now I have to decide on what is f of x. So again, f of x is the function such that I need to plug 16 plus h into it. So it looks like I'm plugging 16 plus h into the square root of x. So again, to be sure, what I want to make sure is that this is f of 16 plus h. Well, that's correct. I'm just taking 16 plus h and replacing it with the x here. So this quantity here must be f of 16. And so taking 16 and putting it underneath the square root is going to give me the value of 4. So the numerator really is f of a plus h minus f of a, where a is 16. And now in these final two examples, we're going to be using this other definition of the derivative. And here we have the limit as x approaches 2. Well, if you were to recognize this as a derivative, then the a value is also really easy to find because that's just the number that x is approaching in the limit setup. So in this case, my a value is 2. And then this might just be even easier because the function f of x that I'm in search for is exactly in the top left corner. So f of x is just e to the x. So again, we can go ahead and check. So here we have f of x minus f of a, where a is 2. So f of 2 means just taking the 2 and substituting it into x, over x minus a. So x minus 2. So here's my function e to the x on the problem, and the a is 2 that I'm in search of. And then let's go ahead and take a look at the last one. The limit as x approaches pi over 6 of sine x minus 1/2 over x minus pi over 6. So my a value is what x is approaching. So x is pi over 6, and my function f of x is sine x. And we can also confirm that this is correct. So this would be f of x minus f of a, so f of pi over 6. So f of pi over 6 means taking pi over 6 and plugging it into the sine function. And sine of pi over 6, as you all know, is 1/2. So in fact, f of x is sine x, and x equals pi over 6. So this is another collection of problems that involve the definition of the derivative, and they rely on you knowing both forms of the formal definition of the derivative as the limit of a difference quotient. Alright, so the last part to this section is that we're going to take a look at this theorem. And the first part of the theorem tells us that if f of x equals mx plus b is a linear function, then f prime of a equals m for all a. So let's think about what that means here. If we have some linear function, so this is in slope-intercept form, y equals mx plus b, then f prime of a, the derivative at a for all a, is m, where m is the slope of the line. So informally, what this says is that the derivative of a linear function is always the slope of the line. So if this is my linear function, mx plus b, and I wanted to find f prime of a for any a, so for any x value I plug in, the slope of that line is always m, so the derivative is always m. So just to kind of take a quick example, if I want to find f prime of, let's make it interesting. Let's say I want to find f prime of pi, given f of x is the function negative 1/2 x plus 2. So f prime of pi, I want to find the derivative of the function f at the x value pi. Well, f prime of x, this theorem tells us, is always negative 1/2 because this is a linear function. So the derivative of a linear function is always, always, always just the slope of the line. So f prime of any value x equals negative 1/2. So it doesn't matter if it's f prime of pi, it's still negative 1/2, no matter what. So if you recognize the function to be linear, the derivative anywhere is the slope of the line, so it's the value m. And now the second part of the theorem is pretty much a special case of the first part. If f of x equals b is a constant function, then f prime of a equals 0 for all a. So f of x equals b is a constant function. So another way to write this is that if we're looking at the function y equals b, where b is some number, well, that's just a horizontal line. And remember, the derivative of any line, any linear function, is the slope of that line. So horizontal lines have slope 0. So no matter what x value we substitute in, the slope of the horizontal line will always be 0. So the derivative of a constant function is always 0. So in other words, again, if we're asked to find, let's say, f prime of negative 100, given f of x is the function pi, so f of x equals pi, this is a constant function. So this is just a horizontal line at the value of pi. So on here, it's almost kind of where this is at a little bit. So it's a horizontal line at pi. It doesn't matter that it's f prime of negative 100. F prime of x, any x value, is always 0. So the slope of this line is 0. You can think of it as sort of 0x plus pi. So the slope is 0. Alright, so now we're going to go over a graphical interpretation of that last theorem. So we want to use the following graph of f of x to evaluate the following derivatives. So here's this function f of x. It's a piecewise function. And we're asked to find f prime of negative 3. So negative 3 is the x value. So I'm going to go to x equals negative 3, and I'm going to look at the function. Now the function at 3 is linear. And remember that the derivative of a linear function is just the slope of the line. So let's take a look at what the slope of this line is. So if here's a point on my line, I would be going up 1. So you can see this would be negative 1 here. So right now I'm at negative 3, negative 1. I would be going up 1 and right 1. So I have rise over run would be 1, 1. So f prime of negative 3 would be positive 1, just the slope of the line, because no matter what, I'm on this linear function with slope 1, anywhere from way over here at negative infinity all the way up to this value negative 1, or close to negative 1. I'm always going to have this slope of positive 1. So now let's look at f prime of 3. So we go to the value of 3, and I go up to the function, which happens to be now a horizontal line. So right here at 3, if I'm a horizontal line, the derivative of a constant horizontal line is the slope of the line, which is 0. Now, to sort of build off this concept of a horizontal line, we're going to also take a look at what's going on at f prime of 0. So at the x value of 0, I have on the graph this point here. And remember now that the derivative is the slope of the tangent line. But this is no longer a linear function here at 0, it's a curve. So I'd actually have to think about drawing myself a tangent line. So a tangent line is going to just graze the surface at that one point. So what do you notice about our tangent line? That our tangent line at 0, or the derivative at 0, is this horizontal line, and horizontal lines, as we found from over here, have slope 0. So f prime of 0 equals 0 as well, because the derivative is the slope of the tangent line at a particular point on a curve, and at this particular point 0, the tangent line is horizontal, and horizontal lines have slope 0. So just sort of building off the second part of the theorem above, that a horizontal line has slope 0, so if a horizontal line is our derivative, or is our tangent line, then our derivative must be 0. Alright, final example. So again, we have this function f of x, and we want to find f prime of negative 2. So I go to negative 2. On the function, I have that it is a linear piecewise function here, so this line at -2 has a slope of -1. So let's say here's one coordinate point, I'd have to go down 1 and over 1. And I can see that this line has a slope of -1, so f prime of -2 is the slope of the line because it's just a linear function, so -1. Now let's try f prime of 1. So 1 is right here on the x-axis, and if I go up to the function there, it's also linear, so I'm just interested in the slope of this line, which again has a slope of 1, it's just this time it's positive. So up 1 over 1, right? This one was down 1, right 1, so I'm going to have a slope of positive 1 this time. And then in the last example, f prime of pi. So if this is 3, pi is just a little bit more than that. And if I go up to the function, I have a linear constant function, which has a slope of 0, so my derivative is 0.